So I started recording the class. Now, so we want to look at electric field due to an infinite line of charge. That is, I have some charges distributed symmetrically on this line of charge. So the length is now what? An infinite length. A line of charge with what we can. I'm still going to do the case of a finite length. Now, let me consider a distance here. Okay. I'm coming.
Are you infinite length of charge?
What did you say?
This infinite line or infinite length of charge?
Infinite line of charge. Yeah, infinite line of charge. Like this is an example of line of charge, so infinite. Okay. The same thing. So, yeah, we don't know the length. The length is an infinite length. Okay. So let's say we are interested to find the electric field at this particular point of interest. Where, pay attention, at this particular point of interest. So let me call this point of interest point P. Let me call that point P. And the distance from, we assume this part is the center of the finite, of the infinite length, where from here to here is given as distance A. Now pay attention, to find the electric field, this is what we do first. We take a small portion of this line of charge and find the electric field. Now pay attention, I'm taking a portion that is infinitesimally small, that has a charge of dq. Hello, mute yourself, your background is a little bit noisy. Yes, if I ask you something, you can answer. So this part is having, this small segment I'm choosing is having a charge of magnitude dq. Okay, don't forget that this charge is a positive charge here. Therefore, if I trace the electric field, it will be something like this, that we push away from this point. Don't forget, if I have a positive charge, the electric field, it will be directed away. It will be directed away. So therefore, my electric field here, remember this charge is dq. The electric field created will be denoted as what? dE. And don't forget that what? I can resolve this electric field into two components. Into the what? The or the what? Horizontal component. Are you there? Hello, are you there?
Yes, sir.
Yes, I have this horizontal component. Also, I have what? Vertical component. So this is what? dEx, also dEy. Now I want to take a look at something. If I should consider this other segment, because whatever is here is also here. So if I consider this other segment, you will observe. So you can ask that, why do I consider the top? Why not the bottom? Okay, let us clear it out. Let me say I'm picking another small segment of this infinite line of charge with magnitude dq. Remember, if I trace the electric field will also push out from this point this way, right? So I also have what? dE. Now, don't forget, if I resolve this into two components, check. This will also have horizontal components. But check, look at the vertical component. Something will happen. The vertical component, dEy, if you observe, look at this part here. It's going in opposite direction to this. Therefore, the y components will cancel out. So there is no y component here. It means that the next electric field on this infinite line of charge is equals to what? The electric field in the x direction. That's Ex. Is equal to what? Ex. Ey will cancel out. If you pick another point, check Ex, Ey. You observe that the Ey will be in opposite direction, they will cancel out. It's good. So distance, let me say this distance from this point to this point is given as r. So I'm just considering one point now. And I will look at only the x and not the y, because y will always cancel out. Let's go. What is the formula for the electric field? Don't forget, electric field E is equals to the magnitude kq over r squared. Now, I'm having electric field dE. So what will it be? It will be k dq over what? R squared. Don't forget, the electric field here I'm having now is dE. So I have k dq divided by r squared. Now, check something now. You see, let's assume that the distance from here to here, this distance from here to here, let's say the distance is x. Now, observe this triangle. You will observe that by Pythagoras theorem, your r will be equal to square root of a squared plus x squared. So I want to replace this my R with that. What will I be having? I'll be having what? K dq over my R is now what? Square root a squared plus x squared. Thank you. Square root of a squared plus x squared. Then there's a square on this R. So I put the square. So this will cancel out. So I have dE equal k dq over a squared plus x squared. Now that we found the magnitude of the electric field, the next thing is that we should find it in vector form. Now, pay attention. Hold on. You see, it is possible that you'll be given something like the linear charge density. If they give you linear charge density, what do? Hold on. Don't forget that what my linear charge density lambda is equals to what? Q over L, right?
Yes.
So, okay, hold on. The charge enclosed here, I'm coming. Is it okay? The charge here is dx. The length of this charge here is dx. So remember that this is Q over what? L. So because I'm looking at this small segment, I'll be saying therefore my lambda is equals to what? dq divided by dx. All together.
Yeah.
Okay. So don't forget from here, my dq will be equal to lambda dx. This, are you following? There are some cases where I'm doing this good. So therefore, let us plug it in this one. What do we have? We have dE equal to k. What is now my dq? Lambda dx. Good. Over a squared plus x squared. All together.
Yeah.
So from here, what do we now have? Now, we found this dE already. And remember, after finding this dE, what do we normally do? Well, let's say the angle to the horizontal here is theta. And that angle is which is also theta. Now, check something else. Stay. Mute yourself, please. Good. Now, you see from this triangle, A is here, this is also the same thing as A, and I have my R here. What's cos theta from this triangle? Cos theta is equals to what? Adjacent over hypotenuse. My adjacent is A, my hypotenuse is R. And so my cos theta is equals to A over, what's my R? My R is square root of A squared plus X squared. So keep this one somewhere. Keep this one somewhere. Now let's go. I've found my dE. Remember, after finding dE, the next thing is that I will resolve it to the horizontal and to the vertical. So to the horizontal, and remember I told that the vertical components will cancel out. So we don't have to resolve the electric field to the vertical again. So we are just using the horizontal. So dE x, don't forget, is equals to what? dE cos theta that I resolve to the horizontal. Therefore, what do I have here? I have dE x equal to, my dE is what? K lambda dx over a squared plus x squared cos theta. What's my cos theta? A over square root of a squared plus x squared. What will this give me? This will give me what? I'll be having k a lambda x. Sorry, k a lambda dx. K a lambda dx all over. This and this will give me a squared plus x squared raised to power 3 over 2. Now, this is what I have. Now, remember, what I have here is my dE. Now, pay attention that what dE is just for this small segment of this charge. Now, how do I now sum up all these tiny segments throughout the infinite length? Then, I'll be using the concept of integration. What will I do? My total electric field, EX, will be equal to integral of the EX. That is, I'm summing up all the tiny segments throughout the infinite length. And pay attention, I said throughout the infinite length. What does that mean? Your integration will have a boundary from negative infinity to positive infinity. You can do it like this. Or you do it this way, that your boundary should be from 0 to infinity, and you are doubling it twice. Let me explain that. Let's say this part here, this center here is 0 to positive infinity. Remember that 0 to positive infinity is that one segment, and whatever you see here is the same thing as this one. So if you integrate one part and you double it, it will give you the rest, it will give you everything. That's it. So I can say integral from negative infinity to infinity is the same as me saying 2 integral from 0 to infinity. So I love the idea of 0 to infinity. So I'll be using this. So what do I have? I have 2 integral 0 to infinity. Now check something out too. You see, what is my dE? My dEx. What was it? Everything that is here. So don't forget, K, A, lambda are all constant. So I have dx over a squared plus x squared, then all raised to power 3 over 2. Now, what do we now do from here? Okay, so what do we now do from here? Okay, you see this integral? I will not evaluate it here because of time constraints, but I will tell you what the integral is. This will give me 2ka lambda. You see this integral is going to give you this answer, x over a squared bracket x squared plus a squared raised to power what? 1 over 2. Then you put your limit 0 to infinity. That's it. Therefore, my electric field Ex will be equal to 2ka lambda. Now pay attention. Firstly, if I substitute 0 for x here, everything here will be 0. So let me just focus on this infinity. Now, to do this infinity here, see what you will do. First, you see this a, I can first move it out over a squared. So to evaluate that infinity, you say the limit as x tends to infinity. This will be the best way to do it. Then x all over x squared. Let me even write it this way. X all over square root of x squared plus a squared. So let's evaluate this. Now that 0 will just go away. So that 0 is just 0. So let's evaluate this. So I have Ex equal 2k lambda all over a as the limit of x tends to infinity. Now divide through by x squared. No, divide through by x, sorry. Divide through by x. Don't forget limit to infinity in your MCH. To evaluate this, you divide by the highest power of x, and that's x. So divide by x all over. By the time I put x inside this square root, it will become x squared, then plus a squared over x squared. So I have 2k lambda over a. This will give me 1 over, here will give me 1. And a number divided by infinity is 0. So everything here give me 1. Therefore, my final answer is electric field. The net electric field equals to what? 2k lambda all over a. 2k lambda over a. This is for what? Infinite length. Did you see that?
Yes, sir.
So if you are asked to find the electric field due to an infinite line of charge, this is what you are doing. Or a charge of infinite length. This is what you have to use. 2k lambda all over E. My lambda is Q over L. You know that one already. The total charge divided by what? Exactly. So you even be given. Because normally we don't know the length of this. Will be given. So this thing is not like it's not for you to cram. It's just for you to say, okay, see how to evaluate the electric field. You can just pick a small segment and just be solving this way, and that's all. It's just something simple. There are a lot with finite length, a lot of them. What should I be doing then?
So I will come out in exam.
Okay, you want to come on. No problem. We'll be solving questions then. Okay, so we have finite length for all those ones, but let me just skip those ones and go to what is more important. Okay.
Yes,
but before
sir.
that, let's look at electric field. Okay, let me give you the formula for finite length.
Okay.
I'll just give you the. I will not prove it for finite length. Good.
Yeah.
For finite length, I will not prove that one. So this one has a particular length. So the answer is electric field E equal K lambda L all over A, well, times 1 over the length divided by 2 square plus A square goes per half. But you see this formula, let me tell you what I assumed when proving it. The assumption is that you see that A is from exactly the center of the rod. A is the distance from the center of the rod to the point. So I assume that this was at the center. If it's not at the center, your integration will be very bulky. So I just consider this simple case. Well, when we are solving questions, we will know how to use this formula, okay?
Yes, sir.
Next one, let's look at due to a charge draining. I will not prove that one too. I will not prove it. Electric field due to a charge draining. Due to a charge, I will not prove it because. So let me show you the chart. Assuming I have this kind of ring, and I do this to turn it to a ring. Okay. So let me say this is the center of the ring, and then I want to find the electric field at this point of interest P. Okay. So picking a tiny positive charge, that was the way I proved it. By the time I draw this, so you push it the E. So that's what I do while going about. So the center of the rod along the x-axis, this is the distance x. The distance from this point to this point is what I give you as R, and this, the radius of the ring is A. The internal radius is A. So therefore, our electric field E, the magnitude is what? KXQ. That this X, you can see what is standing for. Then all over x squared plus A squared to the power of 3 over 2. So this is due to a charge drain. This is the formula you use. So we'll be solving questions later. So let us go to the next aspect. Any question?
No, sir.
So you might not see all this. That's why I'm not dwelling on it, because your school did not really consider it. So let us look at electric flux.
Okay. Yeah.
Let's look at electric flux. Now pay attention. You should go straight to the point. Let me assume that I have a plane of loop around this side. This is a loop I have around this side. And I have some electric field lines entering this loop. I have some electric field lines entering this loop, EA, such that, you see, the plane of the loop is perpendicular. Just observe the condition, is perpendicular to the field line. The plane of the loop is perpendicular to the what? Like, let me say this is the plane of the loop now. It's now perpendicular to the what? To the field lines. Now, pay attention. What is the electric flux? Here, the electric flux, phi. The electric flux is equal to the electric field times the area. This is when they are actually, the electric field lines is what is entering the loop perpendicularly. So if I say electric flux, what am I trying to say? If I say electric flux, I'm talking about the field lines, the amount of the field lines entering this loop. The amount of field line, it might not be a circular loop, it might be a rectangular loop like this, there's no problem. All together? So if I'm saying that, okay, how many field lines are entering this loop? That's when I talk about what? Electric flux. Are we together? Are we together?
Yes, sir.
Hello, are we together? Yes, so if I'm saying electric flow, we are saying that what? It is a measure of how much electric field line are you there that penetrates a surface. Are we together? The amount of what electric field line passing through a surface is what we refer to as what? Flux. Now, when it is passing through perpendicularly, this is the formula. The flux equal to what? EA. Electric field times the what? Times the area. But what of if this is not perpendicular? Okay, let's say it is entering. Let's say it is entering this way. Let's say it is entering this way at some angle. At some angle. Let me say the angle here is theta. Now pay attention. Let me say there is a particular line that is normal to this surface. So let me say this is the normal to the surface. And all these lines are entering at some angle theta with the normal to the surface. How do you find the flux? To find the flux here, you are going to say E dot area vector. That is electric field vector, the dot product of the electric field vector times the what? Area vector. And how do we find this dot product? Is equals to what? EA cos theta. Let me simplify it. If they are entering at perpendicular, when they are perpendicular to each other, what do we say? The electric flux is what? EA. But if they are not, if they are entering at an angle theta inside that surface, what do we say? The electric flux is equals to what? EA cos theta. That is cosine of the angle in which they are what? You know, they are entering through that. So together. So this is how to find flux. Any question?
No.
Now, next is that what is now Gauss law? What is now Gauss law? So what is now Gauss law? What is now Gauss law? What is now Gauss law? Now, pay attention to that what. You see, Gauss gave us the relationship between electric charge and electric field. It is a more general form of Coulomb's law, actually. And what does Gauss law state? It says that well, the net flux, what did I say? The net flux through any closed surface. The Gauss law states that the net flux through any closed surface, phi. The net flux phi through any closed surface is equal to the closed integral check. If I'm looking at a closed surface, I'm using this type of integral. Then the electric field vector dot the area vector, this. And this flux is equal to the total charge enclosed in the surface divided by the permittivity of free space. This is the statement of Gauss law. The net electric flux is equal to this, which is equal to the total charge enclosed in that surface. That closed surface can also be called Gaussian surface. Can also be called Gaussian surface. So the total electric charge enclosed in the Gaussian surface divided by what? The permittivity of free space. Now, let us not take, for instance, if there is no charge enclosed in the system, let's say this E now is equal to 0. We are looking at a case whereby the closed surface enclosed no charge. What do we say? The electric flux is equal to 0. All together?
Yeah.
It's just like I'm having 0 divided by E naught. What will be my answer? 0. Yes, yes.
Yes.
Exactly. Okay, good. Also, take note that what the flux is independent of the shape of that surface. Look at it. This is a loop. This is a rectangular surface. It does not mean. So the flux is independent on the shape of the surface. And if there's no charge enclosed in the Gaussian surface, our electric flux is equal to 0. Now, pay attention. Let us now look at where we can apply what Gauss law in a spherically what symmetrical charge distribution. Good. Symmetrically what? Charge distribution. Okay, let's take for instance that, pay attention. Let's take for instance that I'm having an insulating sphere. I'm having an insulating sphere. Now pay attention, this part is very important. I'm having an insulating sphere, and this sphere encloses some charges. This sphere encloses some charges. Now pay attention. The radius of this sphere is given as R, capital letter R of the Greek sphere. Now, the question is this: how do we go about it when they ask us to find the electric field inside this sphere? How do we do it? Now, we want to find electric field at some point away from the center, but that point is still inside the sphere. Let me say at this point. Now, at this point, what you are going to do is that what you are going to draw a Gaussian surface around that point. Altogether, let me say we have to find the electric field at a point away from this center. What do? We draw a Gaussian surface with radius of r, small letter r. Now check. In this case, our r is less than this big R. We want to find the electric field inside this Gaussian surface. So what do? I will explain that again. You want to find electric field inside this insulating sphere, whereby your R, the radius of this broken curve, this Gaussian surface that you constructed here, where it is still inside the sphere, where R is less than big R. That is case 1. Now, what do we do here? Now, pay attention. Pay attention. Don't forget that what according to Gauss law, what do we say? EA is equal to the charge enclosed divided by the permittivity. Now, the question is this: how do I find the charge enclosed? How do I find the charge enclosed? You see, I will use the idea of the volume ratio here. What's that idea? I will say, okay, to find the charge enclosed, now observe, I'll say the ratio of the charge, I'll say the charge enclosed is equal to the total charge times the volume ratio. That is the volume of the Gaussian surface divided by the volume of the total sphere. Now let's go. What do we have here? Now the charge enclosed is equal to the total charge Q. The volume of this Gaussian surface is the one with radius R. That's radius of its volume of its sphere, 4/3 pi R cube. All over the total volume of this sphere is 4/3 pi R cube. Are we together? So if this, yes, if this cancels this, so it means that my total charge enclosed is equal to the total charge R cube divided by R cube. So I'll be putting it here. So what do I have? So I'll say E, this area is the area of the what Gaussian surface, and the area of the sphere is 4 pi R square, equal to our charge enclosed is Q R cube all over R cube, and this epsilon naught will still be there. So what do you think I will do from here? It's very simple. You see, firstly, this R square will cancel one of these, so you have it. You have one R left. And by the time I divide both sides by 4 pi, I'll be having E will be equal to 1 over 4 pi E naught. Then what do I do? Times what? R divided by R cube. And from here, what do I do? Q is still there. QR divided by what? R cube. And observe, what is 1 over 4 pi E naught? That's equal to K. So my answer here is KQR all over what? R cube. Look at this formula. Is the formula to find the electric field in an insulating sphere. If that point that you are finding the electric field is inside this sphere, you are going to use KQR over R cube. K is 9 times 10 to the power 9. Q is the total charge enclosed. Q is the what? Total charge in this sphere. Sorry. Q is total charge in this sphere. R is the radius of, let me say, you have to find the electric field at some point away from the center. That's a small radius. While big R is the total radius of this sphere. That's how you do it. Now, what of the second case whereby you have to find the electric field at some point outside. Of course, there are still some charges enclosed. Now, assuming I want to find the electric field at this point, what do I do? Don't forget, my radius is still big R. I want to find the electric field at some point outside this insulating sphere. What do I do? Don't forget the gist. Construct a Gaussian surface from that point around this sphere this way. Construct this Gaussian surface. Are we together? If you observe now, from here to here is my small r. On this case now, R is bigger than R. So what do? Don't forget the statement of Gauss law. From Gauss law, EA from Gauss law, EA equal what? The charge enclosed divided by what? The permittivity. All together? All
Yeah.
together?
Yes,
Okay.
sir.
Now, do you know that on this empty space here, there is no charge enclosed here? You see this part? There is no charge outside this small space. There is no charge here like this. It means that the total charge enclosed is still the total charge I have. So this Q is still the same thing as this big Q because there's no charge here at all. Are we together?
Yes.
So yeah, there's no charge at all. There's no charge here. So the total charge enclosed by this Gaussian surface is the same thing as the total charge that I have in this sphere. So I still have my Q. So what do I do from here? E 4 pi r square equal to the total charge Q divided by this. Therefore, from here I have E equal to Q over 4 pi r square epsilon naught. And don't forget, what is 1 over 4 pi E naught? That's what K. So I have KQ divided by R square. Now, if you are to find the electric field, at a point outside the Gaussian surface, your formula is E equal KQ over R square, where R is the radius of the Gaussian surface. But you have to find the one inside the sphere with the formula you are making use of. Now, I have something to do again. What is that thing? Now, pay attention. Assuming you were given the volume charge density. This volume charge density is given as what? Rho. And what's the formula? Is Q over volume. We have done this thing before, right? Exactly.
Yes.
Okay, now let's look at case 1. Inside the sphere, inside the insulating sphere, what's that formula that we proved? We said E equal to what? Do you remember? Inside the insulating sphere, KQR over R cube. I mean now.
Yes.
KQR over R cube. Good. Now, don't forget, from here, my Q is equals to volume charge density times V. So I have K rho V R over R cube. Now, from here, what do? Pay attention. I have K rho. What? Look at this volume here. This volume is volume of the whole sphere, and that's 4 over 3 by R cube. Volume of the whole sphere. Then small r divided by big R cube. So this will cancel this.
Yeah.
My K is written as 1 over 4 pi E naught. This one, of course, will be given, or they might ask you to find it, times 4 over 3 pi. Then I have R. What happened? 4 pi cancels 4 pi. 4 pi cancels 4 pi. So therefore, my formula is what? Rho R divided by 3 epsilon naught.
Okay.
But inside the sphere, there are some questions that they will tell you to find the volume charge density. So you can just use this. So this is it. And that is the end of this. So let us solve some questions.
Okay.
We started by 5 o'clock, right? Okay, 6
No,
o'clock.
but yes.
Okay, let's solve some questions, please.
Okay.
Majorly, let's focus on this Gauss law. Okay. Let me just say some problems.
Question.
Let me just say you're given a problem whereby you have this type of field line with electric field to be equal to 15 Newton Coulomb. So you have the direction here, and we are looking at it entering this surface, and this surface has an area which is 80 meters square. So how do we find the electric flux? It's simple. Our electric flux here, don't forget, is equal to EA. This is perpendicular to this. So what do we do? That's 50 multiplied by 80. What do we have? Our flux equal to what?
For
400.
40. Okay, 50 times 80.
Yeah, Newton meters square per coulomb. That's flux.
Okay.
Okay, that's how it is. So there are some multiple choice questions that I'll send to you. Okay, look at this question. We were told that this is another question that an insulating sphere. Okay, let me put it here. So this question 2, that you have an insulating sphere of radius 2 meter. Yes. You have an insulating sphere of radius 2 meter. You have an insulating sphere of radius 2 meter contains plus 50 microcoulomb charge of electric charge uniformly distributed throughout the volume of the sphere. So question A, you asked, they said, what is the electric field? 1.5 meter away. From the center. One 1.5 meter away. So the next question B, they tell you that what is the electric field 3.0 meter away from the center of the sphere. So look at this question. So let's solve. So they said about an insulating sphere of radius 2 meter. Let's sketch an insulating sphere. We have this insulating sphere of radius 2 meter. So the radius of this sphere, you have it to be 2 meter. That's our big R. R equal what? 2 meter. They told us that it encloses a charge of this, no problem. Uniformly distributed, there's no problem. So this charge is uniformly distributed. So what does that what is the electric field 1.5 meter away? Now the total radius is 2. It means that 1.5 meter will always be inside this sphere. And don't forget, from that point, you want to find the electric field at this point. Look at the Gaussian surface. Our R is what? 1.5 meter. The total radius is 2 meter. And you want to find the electric field 1.5 meter away from the center. So 1.5 can never exceed the outer sphere. It will always be inside this sphere. So therefore, they are giving us question on case 1, where R is less than R. And can you remind us of the formula? What formula to find the electric field? They are looking at inside the sphere. What do we have? Tell us.
R is less than that would be KQ over R squared.
What is it?
KQ over
That is
R
for
squared.
outside. That is for
Okay.
outside. Yes, inside.
Okay,
What do you say?
KQR over R cube. KQR
KQR
over R cube.
cube. So I have 9 times 10 to the power of 9. Times what is my Q? What do you have as the Q? I have
50
50,
times
50 right?
minus
Times 10 is
6
power minus 6
minus
times. What's the radius? 1.5.
yeah.
All over 2Q. So from here, you will get your answer. You will get your answer. That's the electric field.
There's
Now,
no
that's
we
for
just
question.
now.
What do you say?
We just is 2, right?
Yes, that's the big radius. Yes, that's 2 meters.
But you wrote 1.5.
What is it?
You wrote 1.5.
Yes, now you know that this is the small radius. That is the
Oh yeah,
radius
yeah,
that
yeah. I get that.
exactly. So what do we have?
Okay. Now I think that's 15 times 450 times okay. 1.5. 450 times 1.5. That's 675 times 1000, I guess. Okay, divided by 8. That is, it's 4,375.
Okay.
84,375
So
newtons
you
per.
get your answer. I don't want to show you the step. That's it. Next, you want to look at a point outside this sphere. Now I have a sphere, and you want to check with the radius of this sphere. The radius of this sphere is 2 meters. That's the big R. Now, let's go. Now, say that what is the electric field? That's question B. 3 meters away from the sphere. Observe, 3 meters we always get outside. So we want to find the electric field 3 meters away. So from here, construct your Gaussian. So this is where you want to find the electric field. So if you observe this case, you observe that this case R is greater than R. And to find the electric field, you'll be using this formula E equal KQ over
R squared. R squared.
R squared. So that E equal 9 times 10 to the power of 9 times 50 times 10 is power minus 6
Over
our small R is
1.5.
yes, 3 squared. So from there, you will get your answer. That's how to find the electric field. So that's the end of today's class.
Okay.
So I'm sending kind of question that you can practice.
I should send you.
I'll send it to the group. Don't worry.
Okay.
I'll send kind of question that you can practice. So they're like objective questions.
Can you just help me to record this? I need to watch this thing again.
Yes, yes, of course. I will edit the video and send the YouTube link to you. Don't worry. So I've saved the video, the notes already.
Okay.
Yeah.
All right. Thank you, sir.
So yeah, take care. So we continue in our next class.
All right, sir.